So let's practice the chain rule with these examples here. So we're just going to find the derivative in each case. Okay. So if I want the derivative, I'll just call it y prime. All right, what I have to do is notice the structure of this function. Again, it's like before. It's a 4x plus 5 all raised to the 5th power. So basically we have something raised to the 5th power is our most outside look at this. So that means that it would be 5 times that something, 4x minus 5, now to the 4th power, times, and then I have to go inside and take the derivative of that something. So I get 5 times 4x minus 5 to the 4th times the derivative of 4x minus 5 is 4, and I get 20 times 4x minus 5 to the 4th. Okay, so that's how we did it like before. Let's keep going. All right, if f of x is 4 times 3x minus 1 to the negative 2. All right, this is really very similar to the ones from before because I basically have a 4 times something to the minus 2. So I have basically 4 times something to the minus 2. If I do my power rule first, I get the minus 2 times 4 is minus 8. Then I get the something, 3x minus 1, and then I do minus 2 minus 1 is minus 3. Then I have to go inside and deal with the something that was there. So then I need the derivative of 3x minus 1. So minus 8 times 3x minus 1 to the minus 3, and the derivative of 3x minus 1 is 3, and so I get 3 times negative 8 is negative 24, 3x minus 1 to the minus 3. Okay, and so that's working very similarly. How about something like f of x is the square root of 1 minus x squared? Well, actually, that's very similar to what we had because remember, I should rewrite that square root as 1 minus x squared to the 1/2. Okay, so f prime of x is then, now looking to do the derivative, again, I basically have something in my 1 minus x squared to the 1/2 power. So I would get 1/2 1 minus x squared to the 1/2 minus 1, which is minus 1/2, times, then I go inside, what I was holding was the 1 minus x squared, I need the derivative of 1 minus x squared. So I get 1/2 1 minus x squared to the minus 1/2, and then the derivative of 1 minus x squared is 0 minus 2x, so minus 2x. So I end up with the 2's canceling there, getting negative x over, or no, let me not write it that way. Hold on. Negative x times 1 minus x squared to the minus 1/2, which is one way you could write this. Or if I wanted to go back to the root notation, this could be negative x over the square root of 1 minus x squared. Again, it depends on what we want to do with it. Okay, here's a good one here, because it doesn't always have to be a power on the outside. So let's take a look. Here I have cosine of 2x squared minus 1. The cosine is not cosine of x times 2x squared minus 1. It's cosine of 2x squared minus 1. So on the outer look of this, it's cosine of something. So if I'm going to take the derivative, now let me go to the other notation, dy dx. If I'm going to take the derivative, I'm really taking the derivative of cosine something. Well, that should give me minus sine something. So I get minus sine of 2x squared minus 1, and then I have to go inside and take the derivative of what was inside 2x squared minus 1. So I get minus sine 2x squared minus 1 times, and then the derivative of 2x squared minus 1 is 4x. So I end up with minus 4x sine 2x squared minus 1. Okay. How about g of x equals e to the x squared? So still, I have to see what is going on here. And basically, I'm seeing that this is basically e to the something. Okay. So when I go and do the derivative, I think, okay, e to the something, well, I know e to the x gives back e to the x, so e to the something should give itself back e to the x squared. And then the going inside really corresponds to going into the exponent here. So the next thing would be times the derivative, oh, I'm using prime notation here, times the derivative of x squared. So I have e to the x squared, and then the derivative of x squared is 2x. So I get 2x e to the x squared. So although we say inside, inside means into the next layer of the function. Okay, before we do more examples of this, I want to bring in a new derivative just so we can use it and see it in the chain rule as well. So what we're going to look at here is the derivative of the natural log function, okay, ln of x. So again, this is something that I'm telling you, this is the derivative, I'm not proving it here for you. All right, so we're going to say the derivative of ln of x is actually, surprisingly, 1 over x. Okay, that's it. That's what we're looking at right now. The derivative ln of x is 1 over x. Now, I'm going to mention some logarithm rules that, not derivative rules, but just a manipulation of logarithms that will be very useful for us. So recall that the ln of the product is the sum of the ln. So ln of AB is equal to ln of A plus ln of B. ln of the quotient is the difference of the ln. So ln of A over B is ln of A minus ln of B. And ln of A to the B is B ln A. These are not derivative rules. These are just manipulations of logarithms. Okay, but these are going to be very helpful for us before we do derivatives. Also, please remember that ln of A plus B cannot be simplified. So I'll just say cannot be simplified. Okay. All right, so let's see how this would work and how we can make it nicer sometimes using those. Find the derivative. Oops, this should not say f prime. This should say just f here. Okay, so f of x is ln of 5x minus 2. All right, so what I'm going to do is, I see that it is ln of something. Okay, so ln of x says 1 over x. So when you do the derivative of ln of something, it's really 1 over something. That's how it starts. So what I'd have here, if I do the derivative, is 1 over 5x minus 2 times, and then I go inside and take the derivative of that. So the derivative of 5x minus 2. In other words, 1 over 5x minus 2 times 5, or really 5 over 5x minus 2. And there is my derivative. Okay. So now when we go to this one here, now it's ln of x plus 1 cubed. Now while I could do it as ln of x plus 1 cubed, it's actually easier if I make a simplification based on these logarithm rules, specifically the exponent rule there, which says that I can rewrite this as 3 ln x plus 1. I know it looks like the product rule from the power rule from derivatives, but it's not. That's just a logarithm rule. I haven't taken any derivatives yet. Now, when I go take the derivative, I'm going to do it off of this. I just have a constant multiple 3, and then I have ln of x plus 1. So ln of something, so times 1 over x plus 1, times, go in and take the derivative of x plus 1. So I have 3 times 1 over x plus 1 times 1, or I just get 3 over x plus 1. Okay. Now notice, if I actually did, so I'm just in a little side space here, if I did the derivative as ln of x plus 1 cubed, I could have said, okay, it's 1 over x plus 1 cubed times the derivative of x plus 1 cubed. But that would be 1 over x plus 1 cubed. The derivative of x plus 1 cubed is a chain rule itself, so it would be 3 times x plus 1 squared. Take the derivative inside of x plus 1, I get 1. And what we notice is, after cancellation, that's going to give you 3 over x plus 1. And I actually get the same thing as I got before, but it was a little simpler if I did the early transformation. Just like here. If I want to take this derivative, I don't think I want to do ln of this, all that mess inside, because that's going to be terrible when I have to go and take the derivative. I can actually say that this is ln of a quotient. So this is ln of x times x plus 1 minus ln of 2x plus 3. Going even further, this is a product, so I could break that as ln of x plus ln of x plus 1 minus ln of 2x plus 3. Now I'm going to start taking the derivative. Whoops, sorry. When I take the derivative of ln of x, that's simply 1 over x, plus. When I take the derivative of ln of x plus 1, 1 over x plus 1 times the derivative of x plus 1, which is 1, minus the derivative of ln 2x plus 3, 1 over 2x plus 3 times the derivative of 2x plus 3, which is 2. So I end up with 1 over x plus 1 over x plus 1 minus 2 over 2x plus 3, and there it is. And that was much easier than if I had tried to do it without doing these early simplifications. Ultimately, I would get the same answer, maybe not in the same form, but it would not be as simple. Now, for something like this, I don't need to get a common denominator unless I need to go further. So you can stop there and not get a common denominator.